starting with our Q&A. So our first question is from Duct Tape in the forum. Lots of lovely forum names in this segment. And the question is, one of the strategies that was outlined for CUDA's success was that it ran and worked on developer-grade hardware so developers could learn how to use it. Currently, only very expensive GPUs are supported for Macs. Is Modular looking to follow a similar path to CUDA and support GPUs that people have access to sooner rather than later to speed adoption? Or will premium GPUs be the main focus? Why not start with developer-grade hardware and then work up?
Yeah, so I mean, great question. And the current status is we support a wide range of NVIDIA GPUs, including laptops and a bunch of other stuff. So don't be discouraged from that. I think that the only weirdness and the thing we haven't figured out how to do is decide like how we want to test and qualify all these things. And so I think that people have been a little bit shy about claiming support for all the things if they can't test it. And so I don't know, Brad, do you want to add more color on this? Because I know you've thought quite a lot about this and just both in terms of like what we do, but also how we explain things.
Sure. Yeah. I mean, we've been intentionally very conservative about like what we claim. We wanted to like make sure that anything that we initially rolled out, we fully supported, like in CI, in regular tests, in our nightly pre-submits. Like so we had to start with an initial group of hardware that we fully supported, and that was like the data center class GPUs. But as Chris mentioned, we're supporting broad architectures of GPUs within that. And so like the Ampere, Lovelace, and newer GPU classes, we have support within that in Macs. And so that means that like while we have officially like have a level of support for data center class GPUs, we unofficially support RTX 3000 series, RTX 4000 series. I'm running it on an RTX 4060 for going in and testing out GPU programming models and so forth. And so it's not that we're avoiding consumer grade GPUs. We've just been very conservative on the messaging around that. And so we're trying to like we're expanding our messaging in our documentation, but we do want to address consumer grade GPUs as well.
Yeah, so I think we need to fix this. We need to explain this better. We need to have some way to. So I mean, request mostly for Brad and for the rest of the team is like we need to have classes of support or something and say, we expect it to work on this category of hardware, but it's not tested, and let us know if there are bugs or something like that.
Yep.
But yeah, to exactly the point, I think this is a really key piece of being able to make the tech kit useful and be widely available. Cool.
Makes sense. Thank you. So this is from Lenite in the forum. Julia's ecosystem has offered a mature GPU programming model for NVIDIA and AMD for a few years. Other than Julia is not Python, what's your take on the technical reasons behind Julia not reaching the level of adoption in the AI community to be considered a viable alternative to CUDA?
So this is a trap because you're asking me to say something mean about Julia. So like, I see what you're doing here. So I love Julia. Julia's a great system. I love many of the people that work on it, the folks in the Julia company and things like this. And so, and Newman, so I can't really give you a Julia is bad answer, but I can give you a what we're doing different answer, right? And so, we'll see how that goes. So Julia wasn't as super awesome because it like super JIT compiles and specializes, and it has a bunch of things that give you good performance. One of the challenges with Julia is it's just not super predictable. And so with Mojo, we've really pushed towards making the programming model predictable and simple and reliable and robust. Also, compile times are super fast with Mojo. I don't know exactly where we are, but somebody was telling me that just building in all the kernels for an entire Llama model takes on the order of like a minute with our stack. And so that's JIT compiling, specializing, doing fancy graph fusion, like all this stuff. And so like making that performance of the compiler itself fast is something that we've spent a huge amount of time on and it's architected in. In contrast, like CUDA, for example, it can take an hour just to compile flash attention. And so one kernel, right? So Julia, again, I'm not an expert on this, but those are big factors. Now, I think you say, aside from being not Python, I think that's actually a pretty big factor too. And so the not Python thing in Julia manifests in a bunch of different ways. One of which is syntax, but it's also like arrays that start at 1, and there's a bunch of other things that kind of go in there. And so any one of these things is just additional friction and go into this. Now, I think that the key thing with Julia that I don't have the experience, I can't speak to, is like how Julia has fared at providing AI solutions. And so I think that one of the other key things I've looked at, and this is a failing of OpenCL, for example, is like you can write a kernel in many of these systems, right? But a lot of days, particularly today with Gen AI and like all these things, people want to get like a whole solution out of the box. And so with Max, what we're trying to do is we're saying, okay, well, like if you go to builds.modular.com, for example, you'll see, okay, well, we get like, you can get up and running with an entire long model with very fancy LLM optimizations with like all this stuff put together. And so it's not just about having syntax for GPU kernels. Does that make sense to you? Is that what you're looking for? Or?
I think that you would say anything mean about Julia. What I was sort of trying to get out of this question is sort of, right, sort of Julia taps into LLVM for a lot of this, JIT and everything, which sort of provides you stress to think through some of your blog series. Really looking forward to the MLIR one is, well, how do you build something like an AI compiler? Because I program GPUs in Julia and CUDA, etc. You're essentially doing a lot of low level, like a lot of hand tuning of different stuff. So like, does that sort of just, this is separation, right? Is that where you see sort of like, you can't easily build out an ML compiler in Julia as you could with something like Mojo that sits on MLIR and what have you. But that makes sense. Your answer makes a lot of sense.
Yeah, so I mean, I'm not an expert on Julia. So it's just like, and I cannot tell you something can't be done in Julia, like because anything can be done in anything, right? And all I can say is I'm not aware of anybody doing it. And so like, and again, so separate out what could theoretically be done from what has been done, right? So Modular has built a very fancy Mojo integrated graph compiler, right? And so I don't know, maybe that could be done with Julia. I can't speak to that, but it hasn't been done. And so I think that if it were done, that would help Julia be adopted more and things like this. And so anyway, this is the problem with this question is I can't really speak to like what's going on in Julia land because I haven't kept track and things like this. But if you're happy with Julia, use Julia. Like this isn't it's not. I don't look at it that way. What I look at it is we're trying to build something special and useful for people, and that's how we're focused.
Thank you.
Yeah.
Thank you. And sorry, Newman, I butchered your name. Pronunciation. Okay, so next question from Firas in the forum. What is the mental model when programming using Mojo? When I write CUDA, I am not an expert. I can feel the CPU-GPU interaction and feel like I have control like a manual car and move the data forwards and backwards. When writing PyTorch, I feel like it's an automatic car, but with Mojo, I have a hard time programming. So when using Mojo, what should the mental model be?
Yeah, great question. So in one of the blog posts that I did in the series, I think second or third, I think it was the second one, I kind of dived into what is CUDA? and what the way I tried to express it is that CUDA is not really a C++ language. CUDA is this aircraft carrier of libraries and packages and like all this stuff and the ecosystem and serving components. Like CUDA is this gigantic software platform that's been built up over time. And so when you say when you're comparing things to PyTorch, for example, like PyTorch is a fantastic example. It's a layer even on top of CUDA. Okay. And so to me, for a modern AI developer, my expectations are that you want something like PyTorch, something that's higher level for as much as you can get done. But then you want to be able to drop down to lower levels and write fancy matrix multiplications or other kernels when you have to, when you need to. And so to answer your question, with Max, you get the PyTorch-like experience. And so you can use Max graphs. You can even use them from Python. If you use them from Python, like it feels very similar to PyTorch. And then you can go and you can say, hey, I get automatic kernel fusion, and I get like all these very fancy things out of the box, which is really nice, including a wide variety of operators that are really important for various reasons. But then you can say, hey, if I want to go do a triangular decomposition thingy that Max doesn't provide, or if you want to go implement game of life, you know, on GPU or something, or a ray tracer or something else, you're not limited. And so that's the point where you say, okay, let's go use Mojo. Let's go take full control of the hardware. And when you do that, what Mojo provides as the coding language for the GPU, so writing code that runs on GPU. So the comparison here is to CUDA C++. There, you can start with the extremely familiar programming model that you have on CUDA. So you get thread indexes, blocks and warps, and all this stuff, and you get very low level access to hardware, so you're not limited from anything. But then the cool thing about Mojo is because of the metaprogramming and the fancy abstractions we enable you to build, is you can use ours, or you can build your own completely new abstractions on top of that to make it super ergonomic and easy. And so the thing I think that's really cool about Mojo, and one of the reasons I love what the team's doing, is they're building really cool things. For example, layout tensor and things like this, which I think we have documented now, and things like this, which is amazing. And you can use them, and you get great productivity, and there's lots of benefits from that. But if you don't like them, you can ignore it. You can build your own stuff. And so that I think is the cool thing about what Mojo and Max and this technology stack enable.
Thank you.
And also, you're not just limited to NVIDIA as well. You can run on other hardware like AMD, which we're enabling soon.
Yep. So, but you know, like, we haven't launched this yet, so it's like an open secret.
Cool. From Nick, can you characterize in a few dot points how exactly Max as a project differs from all of the previous projects that aim to offer a hardware-independent compute platform? I've heard several detailed answers at this point that includes your blog series, but not a succinct answer that I could easily share with others.
Totally. So you can read into where I'm going with this blog post by just looking at the counter positioning. So like when I talk about OpenCL, doesn't provide a reference implementation, doesn't provide state-of-the-art hardware support like tensor cores, doesn't provide an AI solution end-to-end, isn't an open platform, or I mean it is, but like anyways, there's complicated. Doesn't have somebody that's like set up in the industry to be neutral and actually work across all the hardware and keep the hardware makers from, you know, their own, you know, natural instincts getting in the way of success. Let's just say, right? And so what Max is really doing, that's solving all these problems, in my opinion, trying to, it's aspiring to, and it's still early. So portability, that's a key thing, right? Portability is not just about, and so I'm writing the next blog post that comes out hopefully this week, that's all written, but needs to be finished, is about TVM and XLA. These are compiler projects in the AI space that are very important. But what they did was they took away programmability, or they made it very difficult and very unfamiliar for how to write custom GPU kernels. And they both, like TVM, for example, you had programmability, but it struggled with tensor cores. And so with Max, we want to make sure that you get the full power of the hardware, but then, and you get portability. But instead of providing portability by providing like this super high level abstraction so you can't control the hardware, and what we're doing is we're saying you can go all the way down to the hardware and then build those abstractions in libraries, things like layout tensor. Right? And so this approach is quite a bit different from previous approaches because it isn't taking anything away, and it isn't hard coding something into a compiler like XLA did. Instead, it's making an open developer hacker playground, so you can like you can go explore and use all this kind of stuff. And so anyway, so we'll still building up to this. I probably have like 3 or 4 different blog posts. Ferdinand is asking about Triton. The blog post coming out this week will be about TVM and XLA. I'm trying to figure out like how much I can cram into one blog post without it being 50 pages long, by the way. The next one will dive into MLIR, and either the next one will be about MLIR and Triton, or it'll be about just MLIR. I have some things to say about MLIR, and I don't know if they'll both fit in, but Triton would be next. And the short version is like if you compare Max to Triton, Triton's really really been very successful in the training space and writing kernels for researchers that want to do training because it's a lot easier to use than CUDA. But the problem with Triton is you only get like 80% of the performance of the hardware. And so it hasn't been widely adopted for inference because when you're doing inference, TCO and cost are the thing. And so with Mojo, we want to be state of the art. We don't want you to be held back. We don't want you to be giving up performance for productivity. So I mean, Nick, you're asking, you've heard multiple different high-level answers, and you want a succinct one. I don't know if that's succinct enough, but yeah, that's a new high-level answer, I guess. Todd's asking, why not provide a mechanism for individual hardware providers to provide a description of their hardware and target the software stack? It's sort of like the solution we use in the video device driver problem, which is similar to the compute problem. And so, Todd, great suggestion. LLVM also sort of has this for CPUs. And so if you dive into the code generation part of LLVM, it has a way of declaratively specifying your CPU instruction set. And so then it can automate the generation of a lot of the code. So we're too early to talk about hardware beyond AMD and NVIDIA, but we're thinking a lot about this. And so let us get through AMD and let's solve the, let's get the stack fully up on NVIDIA, which is coming quite now soon. And then let's launch this thing on AMD and then we can talk about beyond that. But I mean, as many people know, I'm quite the nerd and have a lot of big ideas, and like what we're building naturally goes into solving next generation hardware as well.
Awesome. Thank you. All right. Another question from Duct Tape. What lessons from the Objective-C to Swift transition can be applied to the CUDA to Mojo/Max transition?
Yeah, great question. So I've learned so much from that transition. Let me brag a little bit. Developers move from not everybody, but many teams move from Objective-C code bases to Swift in like 3 years after Swift was launched. Like the adoption was remarkable. Some teams took much longer, and I mean whatever, but that shift was huge. And to me, again, just to brag a little bit, you look at like Python 2 to Python 3. The shift took like 15 years, right? And here you're talking about people that are moving from language 1 to completely different language 2, right? And so the magic of that, which was hard thought, by the way, this was a tremendous amount of hard work by a lot of really great engineers, was to make it so that Objective-C and Swift interoperated. And so you could say, hey, I'm an app developer. I don't have to like start by rewriting my entire application to be able to make things work. Instead, what I can do is I can say, hey, I'm working on a new feature. I will implement this new feature, this new class in Swift, but then leave the entire rest of the application in Objective-C. Okay. With Python 2 to Python 3, you could theoretically do the same thing, and it's like almost the same language, but the problem was that you had to have all of your modules in Python 3 before you could use Python 3. And so all of your transitive dependencies had to be upgraded before you could adopt the new thing. And so for large scale projects, that was a huge pain. So flash forward to today, right? So today what we're doing is we're doing two things. So we're doing the Python Mojo thing, primarily around CPUs. And so we want people to be able to adopt Mojo on CPU. We're also, as you know, and as the question is saying, like getting GPU developers, giving them new options, right? And so we have a couple of different things that are cooking. One is we want you to be able to use like CUDA kernels in your Max graphs and make that super easy so that if you have something big and complicated that's already built out with custom CUDA kernels, you can totally use them. And so you can decide what you want to rewrite. That's very similar to the Objective-C Swift transition. You might say that allows modularity, right? So that's a big piece of it. Second big piece of it is that Max is actually a replacement for basically cuDNN, if you're familiar with that. And so cuDNN is NVIDIA's big, huge library of fixed function matrix multiplications and all the common operators and permutations of a lot of these math functions that you expect in AI. And so Max provides all that kind of stuff out of the box, and it's easier to use, and so that we think is a good thing. It's a replacement for that. Finally, when you get to CUDA to Max itself, or to Mojo to write a GPU kernel, you can like have all the familiar affordances, so you don't have to learn a new way to do things, and so you can keep using thread indexes and things like this, and so you can like learn language, learn the new idioms and things like this, and then over time you can decide, hey, it makes sense to use layout tensor, these higher level abstractions, and so you can learn those progressively. And with Swift, similarly, we did that with Objective-C. We said, hey, well, if you're an expert Objective-C programmer, you know all the APIs on the Apple, UI kit or whatever it is on the Apple ecosystem, move over to Swift and you learn new syntax in that case, but you're not learning new APIs. And so you can bring and translate a ton of your domain knowledge over, and you're learning one new thing, and then you can gain expertise in this. And what I saw is that worked really well. So then Python to Mojo, there's similar thoughts. This is where the Python Mojo interop and a whole bunch of other things like that that are still being slow baked to exist are really important. And so a lot of that kind of stuff all feeds into this. So yeah, so I think this is a good approach, and I think that there are great ways to make these steps incremental, and the more incremental you can make adoption, the better it goes.
Thank you. Another question from Key Lime Pie. One of the factors that made CUDA so popular were the libraries provided for GPU compute, such as Kuft, Kurand, and Kublas. Now that we're able to write our own GPU kernels in Mojo, which is amazing, would there be plans in the future for exporting Mojo libraries with the CABI? Do you think Mac/Mojo have all the ingredients required to provide a great experience for library writers?
This is a lot, so I'm not exactly sure where to take this. I'll try to give you some short answers instead of rambling too much. I would love to see somebody build cuFFT equivalent, so that's something that I personally don't. I know FFTs are awesome and super important, but I don't personally know much about modern FFT design, and so that would be amazing to see somebody explore that, similar to random numbers, etc. The cool thing is that then they all work together in an ecosystem, which is awesome. So that then, is there plans to export Mojo libraries with CABI? I think so. I think that already exists. You can have the export decorator, and so you can do that directly. And so I don't know if anybody has done it, but theoretically, and I'm not arguing anybody should do this, but theoretically you could make like a cuFFT or cuBLAS drop-in replacement API for these libraries that then wrap Max and just are implemented with Launch's kernel using Max and things like this. And theoretically, you could do that. That sounds very painful to me. I don't know why you would do that, because like these APIs are so low level and so nasty. But theoretically, you could do that with the existing CXport stuff. And then the final question is, does Max and Mojo have the ingredients required to provide a great experience for library writers? I think so. I think that there are a few missing pieces that we'd like to build out. So, for example, the ability to get better Mojo Python interop, so that you can move the implementation of a Python module into Mojo. That's something that Joel and various other folks are working on. There's a bunch, so I think it's absolutely, it's got the right ingredients, but it can be way better. And so I think we need to continue to invest in language. So anyway, so this question kind of went in several different components. I'm not sure if I'm really getting a question. If you're on the call, I'm happy to answer specific, but that's a quick answer.
One other thing I'll chime in about those CUDA libraries is we have explored those things in the past, and we have some internal tools to make generating these equivalent wrappers, if you will, for Kurand and Kublas. We'll have more to say about this probably in the next couple of weeks as we start announcing more with our GPU package and how to effectively use these things. So stay tuned on that.
Very cool. One other thing I'll say, just to tantalize you, is that next week is the NVIDIA GTC conference. And so we'll have a bunch of content coming out around that, and that will also be super exciting.
Thank you. Another question from Newman. Many of the AI ASIC vendors like Cerebra, Sambanova Systems, AWS Trainium, Grok, etc., have built out their own AI graph compilers and low-level kernel programming interfaces. Essentially, they have taken a page out of NVIDIA's playbook and are building their own CUDA specifically for their hardware. What's your take on how Modular's vision fits within this growing fragmentation of the accelerated computing software stack?
Great question. So I think this is really the crux of the issue. So, so lesson learned when I was at Google. So Google is working on Google DPUs and the XLA software stack and things like this. The thing I learned, so I learned so many things, some of which will be written this week, but the opinion I came to and the thing I realized is that any one of these hardware makers, they're not competing with CUDA. They're competing with all the AI software written in the industry for H100, for example. Like if you go look at the DeepSeek work, it's H100 specific. It happens to be written in CUDA and PTX and things like this, but it's not even like, they're not even trying for portability. They just have H100s or H800s and they're enabling the heck out of that hardware and going, right? And so now the problem for any upstart hardware maker that wants to compete in the space is that now suddenly it's not just like CUDA or CUDA C++ or something like that you have to have a competitor for. It's like all of the industry software. Now, when you look at any one of these, air quote, CUDAs, they're not really, but if you look at one of these stacks, like for example, Google TPU stack, or you look at any one of these vendor stacks, some of them do a better job than others. Often they're not that great for a variety of reasons, but even if they do a really good job, as you're pointing out, they're only doing the work for their chip, for their company's hardware. And so what they're asking is they're asking somebody who wants to adopt their hardware to do two things: swap out the software and then swap out the hardware, and do those two things at the same time in order to get the benefit of their hardware. And the reality is that's a lot to ask. I mean, obviously some people do this and many of these companies are successful and they have hardware that's being used, but that's a lot to ask. And so I think that when I look at how modular helps with this, there's really a couple of different things. So first of all, we can have max work. Oh, and also I would say the reason is, like, if you pick Cerebras, for example, I love those folks. They have a nice software stack they've been building for many years. They're not going to spend time making that work on anybody else's hardware, right? That's just like, they don't have the cycles to do that. Their job is to make their hardware great, right? And so modular is different, right? So our approach is to be both do this high tech work and be able to do stuff hopefully better than anybody else in the industry can do, which, you know, is a big bold bet, and I have opinions on why I think we can achieve that, but also to do so and enable portability. And so portability is quite important to me because NVIDIA, for better or worse, has all this installed hardware and all these people that really need that hardware to light up and go fast. And no matter who comes out with an amazing chip tomorrow, it's not going to get installed in all the data centers overnight. It'll take time, right? Even if it's 10x better, it'll take time. And so our approach is to say, okay, well, we'll do two things. We'll be state of the art, the best implementation that you can get anywhere on NVIDIA. And so we're not building a worse CUDA. We want to build a better replacement for CUDA, even on NVIDIA's hardware. And that enables people to write portable by default code, that enables like all these things we want. And we meet that market where it is on NVIDIA, but then we provide a bridge off. And so that bridge off is really important, because what that means is we can then give people the power to adopt new software on their existing hardware and be able to measure it and A/B compare and see the benefits and usability and all these things. But then when the day comes, they want to get to something with different trade-offs, different hardware, they can go explore that, and they don't have to swap everything out all at once. They can actually take their investment over. And so another aspect of this that a lot of people also forget about is that even CUDA doesn't provide performance portability. And so if you write your kernels and you tune them and optimize them against A100, typically you have to rewrite them to H100. Same thing with other things like Triton Lang and things like this as well, is you don't get performance portability. And so Mojo provides a lot of this. And so if you build on the abstractions, if you actually embrace that software ecosystem, the layers of APIs, like, you get a lot of software portability. There's no magic, but you get a lot of portability, which means that that we can make this migration and really catalyze and enable a thriving hardware ecosystem over time, which is something that no one hardware maker can do. And so your point about fragmentation is exactly right, right? This is what we're fighting. Fragmentation is bad for software developers because you have to learn a new thing for every chip, which is just onerous. It reduces fragmentation increases switching costs. And while some of these people do a great job on their software, fragmentation also means that you just can't afford to invest as much energy into any one of those software stacks as you can if you integrate across all of them. And so modular is still early in this journey, but I'm very excited about where we're getting, and particularly this spring as we're bringing together the GPU support. This is a really, really key point for the team. So that's a high level answer. I also do, so we'll see how things go, but Newman, they were, again, like I have like this idea of how the blog post series will evolve. I want to do an entire post about why hardware makers building their own software stack is the problem. Because it's like, it's touched on in many of the different posts and the different pieces, but pulling that together into one answer, I think is really important. I think, I don't know, is that like 4 or 5 out? Because I kind of want to get through some of the software system first, but I think it's really not obvious.
Thank you.
Newman, is that helpful?
Thank you. That's very helpful. Yeah.
Awesome. Okay, last question. Not CUDA specific, but have there been any emergent features in Mojo that you particularly like? This is from Duct Tape.
So I'm super excited about Mojo's evolution, particularly now that the team has got, it's not, let's not say fully done, but like GPUs are basically enabled, and so the team's able to start planning again and start making further looking plans, and that's also super awesome. I get excited about like the things that get simpler, and so there's all these things. So for example, so again, it's just a thing that I've been nerding out about recently, which isn't like this is me an engineer speaking, this is not me as like the big vision guy, but we spent a bunch of time on enabling dependent types in Mojo very early on and came up with a solution that used the interpreter and the parser, and it was very complicated and it was buggy, and it led to a bunch of really weird behavior and things like this. And we just recently came up with an approach that defined away a ton of complexity, made things super reliable, explainable, predictable, and now it's something we can build on top of. And so that's something that makes me happy, as you say, okay, there's a capability and it gets better and reduces the experience of complexity of using a language, and that makes me super happy. Beyond that, emergent features specifically, when I think somebody in the community figured out that we had the ability to express conditional conformances, I was just blown away. I had no idea. Like we'd implemented some support for some features, and I had no idea the conditional conformances. I had always assumed that it would be this massive set of features, but through a combination of implicit conformance to traits and a couple of other things, it just happened. And I found this out when refactoring some code, and I'm like, what is this library code even doing? I didn't know you could define self like that. Why are you doing this thing? I was like, it just fell off. This is crazy. And so I think that's, again, to me, that's magic. And so like I love simple things to compose, and so that is like the best example in Mojo that I've seen so far. But I love a lot of the different aspects of this. I also love the work that it's emergent to me, but it's the work folks working on the standard library are doing, or the folks working on layout tensor, or engineers in the team that are making the compiler go fast. They figure out simpler ways to solve things, or like there's so many of these different things that are all happening all at the same time. And so this is just an exciting time for like the language is growing up, and as it grows up, people discover new things they can do, and then that changes your viewpoint a little bit, and then it gives you new ideas. And so this phase of the project is extremely exciting.
Thank you.
So sorry I went over time, Carolyn. I hope it's okay.
No worries. Yeah, that was great. Thank you so much, Chris. And thank you to everyone who submitted such great questions. As I mentioned before, if you have any follow-up questions for Chris, feel free to either drop them in the chat or drop them in the forum, and we'll be sure to get those answered async. Cool. So now I'm going to hand it over to Brian.
Alrighty. Yeah, so I am back again. And this time to talk about a max skim of life custom operation I wrote. I kind of landed here because I've been working just strictly with Mojo for since like last summer probably, and didn't really take too much of a good look at Max itself, because I don't really have anything to do with AI stuff at my regular job, so I didn't think it was really for me. But then I kind of realized that if I'm spending a pretty significant amount of my free time working with Mojo, that maybe I should better understand kind of its raison d'etre a bit better. And I ended up sort of eventually reminiscing about my time in university writing Game of Life in MIPS assembly, and decided that that would surely make a pretty good first project. It's kind of not cliche, so I won't just cheat and look up something that somebody already wrote if I'm struggling, and it's simple enough that I'm able to get it done. And just quickly, in case anyone is unfamiliar with Game of Life, it was invented by the famous John Conway in 1970. And basically, you have this infinite 2D grid, and each sort of like cell or pixel of that grid is either alive or dead at any given time step. And essentially, each time step, its next state is calculated by counting the number of live neighbors it has in the sort of 3x3 sort of square around it. And so any live cell with 2 or 3 live neighbors stays alive, and any dead cell with exactly 3 neighbors will become alive, and all other cells are dead. And kind of an important component here is that the next state of each of these cells is calculated independently at each time step, which means that this is a massively parallel problem, or can be massively parallel, and kind of works out to essentially like some modified convolution kernel. And just for a demo, I guess I'll just show the code here. So,
hey Brian, we can't see your slides.
Okay, sorry about that. I did not notice. Yeah, so here now you see my VS Code, right? Okay, cool.
Yeah.
So now here's the code for it. It's 69 lines, which I think is pretty impressive. I went from basically like I've never written a line of CUDA in my life to getting this done in maybe about 4 or 5 hours, which I think is pretty cool. It really just speaks to just the quality and the usability of what's been created here for Macs. And essentially it's just a big for each, and then for each pixel it's going to count up its live neighbors, which I've implemented like a wrap here. So this is just some extra logic for calculating the wrap locations, and then just does a little branchless trick to count if that particular cell should be alive or dead. And then here we just have a Python file that's running all of it, just with some code for decoding the Parley encoded files, a little bit of Pygame boilerplate, and then the code for actually running the graph. Just have a few arguments for pointing it to a file, whether or not you want it to wrap, the target FPS, and the padding around the pattern that you give it. And also, I guess kind of another thing I thought was really cool is that you can use compile time parameters in your graph. Kind of realized that like halfway through implementing this, and I just think that's kind of really, really cool.
Well, and one of the really powerful things about that is that gets specialized into your kernel, and so this gives you the ability. So here using Python API, you can then say, hey, I have a bunch of optional features in the kernel, but then the branches and all the code gets deleted by the time you submit it to the GPU, and so it gets all JIT compiled and specialized and things like this, which is really nice.
Yeah, for sure. I was pretty blown away. And then just have a quick update function here, just to, because the state is held as a NumPy array, which is then passed into Pygame. So then that's converted to a tensor, executed in the model, and then converted back to a NumPy array, and then given to NumPy to render. So then just a quick demo here.
So what GPU are you running this on, Brian?
I'm just running on a MacBook M3, so it's not actually running on GPU. Unfortunately, I don't actually have a GPU that's Mac supported, so I can't. But Owen from the community did test it for me on his 4090, and it was working flawlessly, which is also amazing if you think about it. That I didn't have anything like you can target hardware that you don't even have basically because
so again, you go back to this point of like we need to explain this better. Like, the 4090 is not a data center expensive GPU, but then also the portability aspect is huge. And this is, yeah, I mean, I'm very excited about the work the team's doing on this stuff, but it's not normal to have that.
yeah, yeah. I think kind of just writing this was a bit of almost a radicalization moment for me with Max, where I just realized just how easy this was for me. And like even just having zero experience with this kind of stuff. And also kind of just maybe poking into the idea of just how Max can be useful for things that aren't just AI and machine learning and that kind of stuff. And basically it would seems to be a pretty good fit to me for basically any massively parallel compute problem that you might run into, frankly.
Yeah.
Yeah, and then just, I guess a more complex example. This one doesn't really fit on my screen, but it looks kind of cool. It's supposedly like a Turing machine pattern, and it's just chugging along just fine. Yeah, so I think that's pretty much it for me. Thank you very much, guys. Yeah.
Awesome. Thank you so much, Brian. This is really cool. It looks like Brad has a question for you.
Oh yeah. Also, just a comment. I know you're trying to like apply 2D convolutions to this. We also have and we haven't exposed it yet. We're working on doing this after GTC. We have a stencil pattern generator that I think would be ideally suited to this as well. Then you could expand out from the for each abstraction to actually like sample from the nearby pixels and have all like the shared memory and so forth, reuse and acceleration on GPU and even I think even CPU. So we're gonna be exposing that. We just haven't yet, and that might even further simplify this example.
Cool. Yeah, cool. Yeah, I think it's interesting. This is very like what I've written here is very like naive solution, so I think it'd be cool to see just how far we could push something like this for sure.
Any questions from the audience for Brian? Cool. Well, thank you again, Brian. Really cool. And then I will hand it off to Hammad.
Okay, yeah, I'm Hammad. I'm a creative developer, and I'm here to talk about a project I was working on. It's a UI development, GUI development library in Mojo. So the goal here was to help Mojo be able to create GUI libraries, expand more into the software development area. So instead of making one from scratch, I instead bound an older C++ library called FLTK. I don't know if and you've heard of it, FLTK. But I decided to create Mojo bindings for FLTK. So it's exactly what it sounds. And again, I didn't build it from the ground up. I instead took FLTK and built bindings around it so that I could bind it to Mojo. And I essentially did this because creating one from scratch would result in a less smaller ecosystem and no cross-platform compatibility, whereas FLTK already offered that. So yeah, I think I should give a demo before I talk more about it. Okay, so to basically get started with CombustUI, you should first install the it's a small utility I wrote. It's called Ignite app, and it helps you install CombustUI on your local machine and start creating new projects. So you can basically install it. There are installation instructions on the website. I'll share the website later. So you can just type Ignite app, and you can just tell it the app name. I'll just call it new app and give it a description. And it'll clone the CombustUI website, CombustUI library, and it'll extract the important parts, and it will eventually result in a file structure, file directory like this with build scripts and the different libraries included. So to get started, I'll give a small tutorial type thing for CombustUI. So first, you have to create this application instance. It basically contains all the code required for getting the application started. You can see over here. So it basically checks if everything is okay, if your operating system has it installed, and it gets the application started. So first, I'll create a window, spawn it. I'll pass in the width, the height, and a few flags. First one is resizable. Second, if I have a frame around it, and third, if it's full screen. Now I'm giving one to resizable because I want my window to be resizable, and I don't want it to have no border, and I don't want it to be full screen. And in the end, I can write the title of the window, for example, new window. Now, one thing you can see is that I had to use as bytes to convert it into C compatible. This was a small issue. I looked into it for a long time, but apparently the string got corrupted for some reason as it got passed from Mojo to C. So I ultimately decided to convert it to bytes. Then we do app.mark pointer as main. Basically, this function tells the application which widget is the main widget, and it makes sure that it's visible and terminates the application as soon as the widget's pointer is destroyed. So it's basic small memory safety. And in the end, we can just type execute. Then we'll just run it. Oh, sorry, I forgot to show the widget. You have to show the widget before you can actually see it on the screen. And here we are. This is a small window. It's actually interacting with FLTK, fully resizable. Then we can actually add more widgets to it. For example, I could first change the color, I guess. So I'll say, so yeah, FLTK has a 8-bit color palette, so you have to convert the RGB values into a single integer. So basically, this is what this function does. It takes RGB values and applies bitwise operators to compress all those individual values into a single int32. Next, I'll just go for white for now, and I'll add a label. At the center, I guess, and I'll make it long enough to show the screen. One thing you can notice is that I didn't need to clear any of these pointers. This is because FLTK manages those pointers on its own, which makes it comparatively a little memory safe, I guess, but it's not that safe. You have to do some memory safety on the Mojo side, and I'll be adding that soon in later versions. Some of the other widgets that we also have here is button. I just create a button here. And give it some text, and again I can run it again. So here we are, a small button. It's fully interactable, and there's also an event system, but it's not actually stable enough, so I cannot demo it right now. But there is a small capability built in for finding events, grabbing events from FLTK, and then fetching the ID from the integer, and then getting the handler. It's actually built in, but I can't demo it because of certain small problems in the latest version. Then there's, I guess that's it about for the current version. There's also other features like images and boxes and drawings, but I can't really demo them because they're, again, not really stable. So you might ask, why not Qt? Sorry about the typo over there. So why not Qt or JDK, something like the big libraries in the market right now? Why a small diminutive library like FLTK? Well, basically, FLTK is really, really lightweight. It has a really small blueprint. It's really easy to understand for literally everyone. And it's really simple to get started. It's no big deal. Like in JDK, you have a lot of boilerplate. You have a lot of pointers you have to allocate. You have to take care of a lot of things to get even a basic button on the screen. On the other hand, FLTK is literally just simple small classes, and plus it's object oriented, so it's really easy to use. So how does it exactly work? So I made a small diagram showcasing how CombustUI actually works. Basically, whenever you call a small command, for example, spawn window, I just called it previously to show a window, it passes the command to a Mojo layer. It's a small layer. In the code, it's the application class. It does this. It performs the function of the Mojo layer, and this layer then passes calls to the C bindings. And the C bindings in turn call the FLTK functions, which pass the pointers back, to the Mojo layer, which give the pointer to the programmer. You can allocate those pointers or show them on the screen. Of course, this is not 100% performant. I'm still making some performant optimization, like batching certain calls and focusing on optimizations such as GPU optimizations, like using OpenGL instead of just using the CPU to render stuff. And that's how it works. So currently it's a really small library. I'm really focusing on making it bigger, better, so that more people can use it and it's easier. But currently I'm focusing on making this rather functional and really terse coding style into a more object-oriented style, which accommodates most people's needs, which helps them code better, makes the code base more maintainable. And secondly, I'm also focusing on adding custom widgets, new custom widgets, not just the ones in FLTK, adding more customization. For example, adding CSS, just like in Qt, we have CSS, we can style it, we can make it even better, make it, and it looks non-native and it's better comparatively, whereas in FLTK, everything just looks kind of weird and hideous. I'm also focusing on making it usable and safe. As you can see, it relies a lot on pointers, passing pointers directly, and that's not exactly the best style of coding. So I'm trying to focus on making it even more safe. And that's about it. Here's the repo if you want to check it out. And this is my library, CombustUI.
Thank you so much, Hammad. That was great. Any questions for Hammad? Okay, well, we really, really appreciate you sharing that awesome demo, and thank you also to Brian and to everyone who submitted questions for Chris's Q&A today. We will see you all in about 1 month. Definitely reach out on the forum if you'd like to speak at our next community meeting. Thank you so much.